Good morning, everyone. The image you see here isn't just a map. It's a representation of the complex, chaotic systems that govern our world, from traffic flow and supply chains to the volatile movements of global financial markets. Beneath this chaos, however, there exists a potential for order, if only an intelligent entity could find the hidden patterns. Today, we are going to explore the blueprint for creating that intelligence, the agent in the shadows. This is the story of how an artificial intelligence, through the process of reinforcement learning, learns to navigate and master environments that are constantly shifting, uncertain, and highly unpredictable. We will trace the agent's evolution, starting from naive attempts at memorization through to sophisticated strategies of adaptive learning, and finally, to the deep intuition required to manage truly infinite complexity. Our core goal is to understand how we can forge order from chaos, not by dictating the rules, but by letting the agent learn the rules through experience and consequence. The power of this approach lies in its ability to solve problems where traditional programming fails, problems defined by endless feedback loops and high stakes. Let's begin the journey of mastery. Every challenge solved by reinforcement learning starts in an arena defined by action and consequence. This environment, no matter how complex, whether it's a financial market, a robotic arm, or a video game, can be broken down into two fundamental entities that matter. On the left, we have the agent. The agent is the decision maker, the lone operator. It observes the system, chooses an action, and executes it. Its sole, singular purpose is to master the system, whatever the system may be. On the right, we have the environment. This is everything else: the market, the physics, the rules, and the inherent chaos. The environment responds to the agent's action and provides a crucial piece of feedback: the reward. The reward is a single, raw number, a score, a profit, a penalty, that tells the agent how well it did. This feedback loop is the engine of all reinforcement learning. The agent's ultimate quest is not just to get a good reward in a single instance, but to forge a policy. A perfect, enduring strategy designed to maximize its total cumulative reward over a long period of time. This dynamic interaction, where an agent learns optimal behavior solely through trial and error, is the powerful essence of reinforcement learning. To understand how the agent begins its mission of mastery, we must first define the system it intends to conquer. For our purposes, we'll place our agent in a volatile financial market environment, running what we call the arbitrageur protocol. A full trading session, from start to finish, is defined as one episode. The first step for the agent is observation. It must define the state, which is essentially the signal it receives from the market. In our simple model, the state is defined by three key variables. The overall market trend: is it up, down, or sideways? Volatility: is the market high or low risk? And news sentiment: is the surrounding news positive or negative? Next, the agent must act. These are the actions, or the play. At any given moment, the agent has only three explicit choices: buy, sell, or hold. Finally, we establish the objective. The agent must execute a sequence of trades throughout the episode that maximizes its total profit. By strictly defining these parameters, the observed states, the available actions, and the measurable reward, we create a structured environment where the agent can begin to learn the optimal policy. The agent begins its quest for mastery with the most basic, rigid strategy imaginable: the ledger system, often referred to as L-learning. This approach is naive, but provides a foundational understanding of state-action mapping. The agent maintains a ledger, an L-table, which is simply a massive lookup chart listing every single possible market state against every possible action. After an entire trading session or episode is completed, the agent calculates the total future reward, or TFR. This TFR is simply the final profit or loss achieved during that session. Now comes the rigid core of L-learning, the update rule. The calculated TFR for the sequence of moves made entirely replaces whatever value was previously stored in the corresponding cell of the ledger. It's an absolute overwrite. The resulting strategy, or the policy, is equally simple. In any given state, the agent always executes the action that currently holds the highest value in the ledger. No questions asked. This system works on the hopeful assumption that the world is stable and predictable, allowing the agent to perfectly memorize the best move for every scenario. While this is a simple concept, it establishes the mechanism of state-action value pairing that underlies all subsequent, more complex algorithms. When we deploy our L-learning agent into a stable, deterministic environment, a simulation where patterns repeat perfectly and unpredictability is removed, the blueprint appears flawless. In this controlled world, the agent quickly identifies the optimal sequence of actions necessary to achieve maximum profit. As the agent runs through episodes, the L table rapidly fills up with high-value plays. For example, as shown here, the agent learns that starting in state A, the optimal move is to buy, which leads to state B from state B. The optimal move is to hold, which leads to state C, and finally, from state C, the optimal move is to sell. This perfectly structured sequence reliably yields the maximum profit of plus 2500. The strategy works with ruthless efficiency because the environment never changes. The agent has solved the puzzle by exploiting known, repeatable patterns. At this stage, the agent has achieved total control, based entirely on memorizing the perfect path. It has an ironclad plan, and its ledger is the perfect map. But this perfect control only lasts as long as the world remains artificially predictable. The fundamental truth of real-world systems is that chaos is not an occasional obstacle. It is inherent to the system itself. To test the agent's resilience, we introduce unpredictability, a market shock, a random, stochastic event that defies the established, memorized pattern. The agent, following its perfect policy derived from its L table, makes its first move action. Buy from state A, but immediately, the market shock hits. The environment is instantly thrown into state X, an unexpected state for which the agent was unprepared. The session immediately ends in failure, resulting in a catastrophic loss of minus 175. This reveals the critical flaw of the ledger system, its absolute update rule. The new, terrible TFR of minus 175 overwrites the previously high-value entry, plus 1138. A single, massive stroke of bad luck has poisoned the agent's entire knowledge base for that state-action pair. Despite having experienced countless successful runs before, the agent has effectively forgotten the correct strategy for state A because of one random event it could not control. This fragility proves that rote memorization is incapable of surviving in a world characterized by genuine uncertainty. The ledger system is obsolete. It is built for a world that doesn't exist. To survive a stochastic world, the agent must evolve and adopt a philosophy designed to handle uncertainty. This leads us to the Q paradigm, or Q learning, an upgrade built upon three essential principles that address the flaws of L learning. First, we introduce adaptive memory through the learning rate, represented by alpha. Instead of simply replacing old knowledge with new experience, alpha dictates that the agent must blend the two. A single failure should not erase a history of success. The new Q value is therefore a weighted average, a mix of the old established value and the newly observed reward. Second, we introduce calculated foresight through the discount factor, gamma. The future is inherently uncertain. Gamma forces the agent to value immediate rewards more heavily than distant, less reliable ones. It discounts future gains based on the chaos and volatility of the environment, making the agent's estimations more realistic. Third, we establish strategic gambles using the epsilon greedy policy. The agent cannot afford to always exploit the known best move, or it will never discover better paths. Epsilon sets a small probability for the agent to explore, to take a calculated risk on an unknown path. This mechanism is vital for adapting when the environment shifts, ensuring the agent never gets stuck in a suboptimal solution. These three factors combine to create a resilient, adaptive, and forward-looking learning protocol. With the Q-learning protocol now in place, let's redeploy the agent into the same chaotic simulation and observe how it handles the market shock. The agent starts in state A and chooses the optimal action. Buy. The market shock hits and we are thrown into state X, the unexpected state. The agent sustains a loss, but the outcome is now a setback, not a fatal crash. Why? Because of adaptive memory alpha, the new low reward is not an absolute overwrite. It is blended with the pre-existing high Q value, lowering the overall value for that state action pair, but preserving the historical success. The Q value is diminished, but its foundation is not destroyed. Furthermore, the agent must now respond from the unexpected state X because of strategic gambles, epsilon greedy. The agent does not remain stuck in failure. It uses its built-in mechanism to try alternative paths. In this case, it makes an adaptive choice to sell. Leading to state Z, the resulting loss is minimal, only -20, compared to the catastrophic -175 under L learning. The agent no longer seeks an unbreakable plan. It seeks resilience. It learns to absorb shocks, continue the mission, and quickly rediscover the optimal strategy even after being knocked off course. Q-learning grants the agent the ability to survive chaos. While Q-learning represents a huge leap forward, it still carries a subtle, constant flaw known as optimistic bias. Q-learning is an off-policy approach. When it updates the value of the current state, it looks ahead to the next state and makes an assumption. It assumes that in that next state, it will always take the absolute best action, the one with the highest Q value, max Q next state. However, remember the epsilon greedy policy. That policy dictates that sometimes the agent must explore, meaning it won't take the absolute best move. Q-learning updates its map based on what it could do, not what it will do, creating that optimistic bias. The final refinement, which grounds the agent firmly in reality, is the SARSA doctrine, state action reward state action. SARSA is an on-policy algorithm. It explicitly uses the action the agent actually takes next, explorations and all, to update its current value. As shown in the diagram, the update uses Q, next state, next action, the specific Q value corresponding to the chosen action, not the maximum possible Q value. SARSA operates based on its own true behavior. This shift makes the agent's learning more conservative, significantly more realistic, and often more stable when operating in the most unpredictable and chaotic systems. It is the realist's approach to reinforcement learning. When we analyze the performance of these two advanced protocols under rigorous testing, running thousands of simulations in a highly unpredictable environment where there's a 10% chance of a market shock after every move, the difference between Q-learning and SARSA becomes starkly clear. On the left, Q-learning, the maverick, exhibits aggressive and volatile behavior. Its curve shows high peaks and deep troughs. It learns quickly because it is constantly aiming for that theoretical ideal path, but because that ideal path is often unobtainable in a chaotic environment, its performance is highly inconsistent. It is optimistic but erratic. On the right, SARSA, the realist, demonstrates a much smoother, more consistent learning trajectory. Because it bases its updates on its own actual behavior, it maintains a grounded, stable path to improvement. Crucially, while it might appear to learn slightly slower initially, SARSA ultimately achieves a higher, more consistent performance ceiling. The realist wins the long game. Q-learning aims for an ideal that might not be achievable, making it volatile. SARSA builds a safer, more stable, and ultimately higher-performing strategy based on what its policy will do, not what it could do. The verdict is clear. The SARSA doctrine provides the superior, robust protocol for achieving sustainable mastery in a chaotic system. We have solved the problem of chaos, but we now face an even greater adversary: scale. Our arbitrageur protocol was simple. It had only 8 total states, 2 trend options, x2 volatility options, x2 sentiment options. Creating a Q-table for 8 states and 3 actions is trivial. A manual lookup works perfectly. But the real world is nearly infinite. Consider a simple 5x5 board game. Its state space is nearly 850 billion unique board positions. The game of Go, which AlphaGo conquered, has more states than there are atoms in the visible universe. For real-world challenges, whether we are programming robotics, managing complex logistics networks, or searching for new drugs in immense chemical spaces, the number of possible states explodes exponentially. This is known as the state space explosion. In such contexts, creating an explicit Q-table, a ledger that attempts to memorize every single state action value, is not just impractical, it is physically impossible given current or foreseeable computing power. The agent's greatest challenge is no longer just surviving chaos, which Q-learning and SARSA taught it to do, but managing the sheer, overwhelming scale of reality. When the map, the Q-table, becomes impossible to store or build, the agent must learn to navigate by instinct. This requires a fundamental shift in our approach. The solution is simple. Stop trying to store the entire map, and instead, train a function that can predict the map's values on the fly. We replace the vast, impossible Q-table with a deep neural network. This is the core innovation behind deep reinforcement learning. The neural network acts as a powerful function approximator. Its input is the current state of the environment, no matter how complex that state is, whether it's 100 sensor readings or millions of pixels. The network processes this complex input across multiple hidden layers, and its output is the predicted Q value for every single possible action the agent can take. For our market example, it immediately outputs the predicted value for buy, sell, and hold. This technology is what powered AlphaGo to defeat a world champion, learning moves that no human had ever conceived. It gives the agent an intuition, a deep, powerful sense of which actions are best, allowing it to navigate a world that is far too complex to simply memorize. Deep RL provides the agent with the necessary cognitive tool to achieve mastery in environments of infinite complexity and overwhelming scale. Let's conclude by summarizing the path we've taken, extracting the core principles of mastery that apply not just to AI, but to any system attempting to optimize behavior in an uncertain world. Our journey began with L-learning, which assumed a predictable world and was doomed to fail when chaos arrived. The first principle is to acknowledge chaos. A strategy that ignores uncertainty is inherently brittle. The second stage, the transition to Q-learning and SARSA, taught us several crucial lessons. We learned to learn from every outcome. Success and failure are merely data points. Through adaptive memory alpha, we blend new experience with old wisdom, ensuring that no single random event can erase a history of hard-won knowledge. We also learn to balance exploitation and exploration. The optimal path is not static. It is found by consistently leveraging what we know works, exploitation, while daring to take strategic gambles, exploration, to discover potentially better methods. Finally, in the face of insurmountable scale, we adopted deep reinforcement learning. This teaches the ultimate principle. When the map is too big, build a compass. When a problem is too vast to memorize or calculate explicitly, we must build an intuition, a functional approximator, that can guide us toward success. These principles, taken together, form the blueprint for creating truly rational, resilient, and high-performing autonomous agents. We have seen the agent evolve from a rigid memorizing system to a resilient adaptive learner, and finally, into an intuitive master capable of navigating vast, chaotic spaces. Reinforcement learning is far more than just a set of specialized algorithms. It is a profound blueprint for creating rational agents capable of forging order from even the deepest chaos. This technology is rapidly moving beyond simple simulations, now driving breakthroughs in fields like robotics, where agents learn physical skills through trial and error, and drug discovery, where agents navigate immense chemical spaces. The philosophical question we face is no longer if machines can master complexity. They demonstrably can, but what role we will define for them. We now possess the capability to delegate high-stakes, highly complex decision-making to systems that learn optimal policies in ways that humans simply cannot match. The technology is proven, the architecture is sound. The question that remains for all of us is this: what challenges will we set for them next?